Hi, I'm Will Jackson. I'm the Director of Engineered Arts. I'm not actually Marcus Holt, if you were looking at the holding slide. I'm going to give an overview of Engineered Arts, who we are, where we've come from. Talk about Ameca here, who is our latest generation humanoid robot. As I'm talking, you're probably going to think of questions, things you want to ask. If I could please encourage you to put the questions in the chat, and we'll try and leave 10 minutes or so at the end of this session to go through. So mechanical engineering, electronic engineering, embedded software, high-level software, artificial intelligence, humanoid robots, what the future is for them. Any of these questions, please put them in the chat. So who am I? I actually studied art and design, so not a formal engineering training. However, I built my first computer at 13 years old, learned to code assembler, and have been building robots since about the same time. From my education, I went out and I started working in special effects, so props, models, building robots for film and television, actually. That was kind of a little bit of it's exciting on one level, but disappointing on another, because everything you make is actually destined just to appear on film, and the physical hardware that you work on always ends up in the bin, and I found that rather disappointing. So I went into, I moved out of special effects and went into exhibition design. We were working on a lot of science education projects, which is really the origin of Ameca, the robot standing next to me. So one of the first robots we created back in 2005, when the company first founded, was called Robo-Thespian. Kind of a bit of a joke. Thespian is a hammy kind of actor, and the purpose of that robot was really to talk to people. What we realized was that the best way to explain, to try and communicate, was talking to people one-to-one. But if you have to do that for 10,000 people in a day, repeat the same thing over and over again, it becomes very tedious. So we thought, actually, this is a task that we could automate. So that was the origin of Robo-Thespian. We now are on version, I think, 3.6 of that series. There are around 130 of them installed around the world. Last time I counted, I think it was 27 different countries that they were installed in. Typical kind of applications for those robots is science centers, museums, visitor attractions, that kind of thing. So what is the use case for humanoid robots? I actually would say it's not really about utility tasks. So don't think about having a robot in your home that's going to be your butler, or going to get a beer from the fridge, or do your washing up. What does a dishwashing robot look like? It's actually probably just a square box with some metal trays inside. It's probably made by Bosch or Smeg, and it costs a few £100. So it doesn't really make sense to have a very expensive humanoid robot to perform those kind of tasks. So what is this kind of robot for? It's all about expressions, it's about gestures, it's about communication, it's about a robot that responds to me, that I can communicate with in a natural way. That's the reason for making it in a human form. I always think that Star Wars is a really good illustration of this. So if you cast your minds back to the original Star Wars film, one that I grew up with, two key robots in that film, C3PO, R2D2. R2D2 is the utility robot, a little round thing with a domey head, looks like a dustbin. Doesn't speak, it bleeps, and it has screwdrivers, and it does useful stuff like fly X-wings and repair things and things like that. C3PO is the humanoid robot that chatters away but doesn't actually do much useful stuff, but is very entertaining. So that's the kind of human interaction robot. There's a very telling scene, I think, in the original film where the two robots are being resold secondhand after being captured, and nobody really wants C3PO. They're more interested in the utility robot R2D2 because those are the kinds of jobs that they've got at that time. So that gives you an idea of what humanoid robots are about, where we've come from. So we started out, we incorporated as Engineered Arts back in 2005, so been around 17 years now, and we had a lot of problems to address. So we wanted to put humanoids, we had it into a public space. They needed to be reliable, they needed to be safe, we needed software frameworks, we needed to tackle all of the embedded hardware, motor control, all of these things needed to be addressed, and it was a huge headache. So we started out, actually our early robots used a lot of fluidic muscles or air muscles, so they were a large amount of pneumatic components in there. Pneumatics was a great choice because it's easy to make it robust, and it's easy to get fine force control, so you can turn down the pressure and you can make your robot relatively safe quite easily. Pneumatics don't work so well for fine position control, so we had a lot of headaches on how do we design valve control, how do we do encoder feedback, and how do we resolve fine position control, this conflict that you get. So here we are now 17 years later, and you will see, actually I'll go through more detail on Ameca later, but you will notice there are still pneumatic cylinders, but this robot is primarily electric and it has no external pneumatic supply. So back to the history a little bit more. RT1, our first one, we couldn't even integrate all of the control onto the robot. So there was a very large umbilical, a lot of pneumatic connections. There was a separate control cabinet. So if any of you are familiar with sort of machine tools or factory installation, it looked a lot more like that, where you would have a separate control cabinet. Very early work, we actually used PLCs before we moved to PCs, so programmable logic controllers. When we moved to a more PC-based framework, early software was very simple. So it was just a database and basically a piece of software that pulled values out of a database, piped them to a robot. So it was just a very simple animation playback system. By the time we got to RT3 and now RT3.6, everything had become very integrated onto the robot itself. We integrated the valves into the body, and we'd actually started a development of a fully fledged robotics framework to address the problems we had on the control side and on the embedded side. So robotics is primarily an integration task. It's how do I get various different actuators, motors, cylinders, etc., sensors, cameras, for example, the two we have in the eyes on Ameca here. We also have stereo microphones in the robot's ears. We can incorporate depth sensors, infrared sensors. You have encoders on all of the joints. We have force sensing on motor drives. how do you integrate all of this together? It becomes a very complex problem. So I'm just going to share screen a moment and give you some insight into the frameworks we use to achieve this high level of integration and get to this level of complexity. So let's just share here and here and that one. Okay, so hopefully you're seeing this. So the first thing you might notice about this is we're looking at actually a web browser. So this is simply Google Chrome, and we'll notice a URL at the top here. And on this system page, we see all of the software that's running on the robot, and we can see CPU usage. We've got this proxy device host here that's nearly using an entire core. That's the motion control for the robot. We could look at the overall topology of the system. So you see it gets pretty complex. If I drag this around, we have hub in the center, which is connecting all of the software parts together, and then various inter-process communications links between them. So coming through, we see various different tabs in here. So control, how do I actually code for the robot? How can I write high-level abstracted functions to produce interactions? So here we have a place where we can basically code directly in Python in the browser, and if I click start, I can start running this code and see, I can get debug and see exactly how it works on robot. Flick over to sensors here, and we actually see what the robot sees, and we see slight view side of my head, looking back towards the monitor and around our studio space here. Devices, for all the embedded engineers, people working on control, this is probably the place where you're most interested. So what you'll see on this page is a virtual oscilloscope. I'm not graphing anything at the moment. Let's find something interesting to have a look at. So I can come down, let's have a look at the position of one of these actuators, and then let's start graphing that. So what we see is this motion graph, and this is actually for the position of an eyelid on this robot. There are 14,800 parameters on this Ameca model robot that we need to set correctly for the robot to run as expected. Now you'll see we've got a very large tree of devices here, of different motion control boards, and we can go down through each of the layers inside here to set individual parameters. This is an Ameca Generation 1 robot. It has 51 actuators. Our Ameca Generation 2 goes to 97 actuators, and you can see how this problem just multiplies. It becomes so much more difficult. So going back to the early days of our RT robots, I think I personally wrote the first servo interface, and it was written in Visual Basic. It was a very ugly piece of software. And we decided early on that it was really important to be able to visualize all of our data, do all of our integration in one place. So over the next 17 years, we strived to try and get everything in one place. So not only can I plot this value for a position, I could also plot software events that are happening either at the embedded level or at high level. So everything within the system is visible. A virtual oscilloscope works really nicely for this kind of 2D data, but sometimes the problem becomes more complex. So we also have 3D visualization. So in this one, we see a simple stick representation of the joints of the robot, and we can see projected into this 3D space what the robot's vision is. If there are people in this space, we can populate 3D models and attributes for those, and this gives us a visual way of debugging what the robot is doing. You'll also notice web APIs. So building a robot is one thing, you also need to control it externally. People often want to interface their own software. So how do you do that? So this particular robot has a RESTful API. So basically we can go through any of the nodes and functions in the robot and we can externally control those. Assets, so motion, speech, so a lot of things we might want to use or reuse. So if I have a look at this one here, let's just see what that does. Okay, Ameca doesn't know what it does. It's actually a shrug. So you can see that I could create motion primitives for my robot, which makes it much easier to build up complex behaviors. I will also show you another online tool that we developed, which is called Virtual Robot. So this gives us a visualization of the robot that we're working on in 3D. And again, this is entirely browser based. So there's no installation. So it doesn't matter if you were running Windows, Linux, whether you're working on a Mac. This software works across platforms because it's entirely browser based. So this has always been our philosophy from the outset of the company to work in this way. You can see that I can actually directly interact with this robot model, and it's a way of creating motion primitives or full animations. I can look through, let's come over to an arm here. Pull that up and you'll see a list of outputs on the side here, or robot inputs, outputs from model robot inputs, and these are the actual control values that would be sent to various motors, actuators on the robot itself. For those of you interested in mechanical design, you'll notice some quite complex, let's have a look at, see if I can pull the neck here. So let's find that in this section. Okay, you'll notice some of the ways the neck can move. There are actually 4 actuators in this neck. If I lean in a bit, let's have a look. So let's get Ameca to track around and have a look at my hand, and we can see a bit more of how that neck moves. And you'll notice sliding across to the side, and the way that neck can lean right back. Hopefully that's visible in the video. We actually have 4 actuators working in parallel here, so it's a kind of minimalized version of a Stewart platform, if you will. So a fixed link in the middle and 4 actuators around the side. Sorry, I was still presenting screen here, and I'm going to stop doing that and come back. So yeah, so looking at the actual robot, so following my hand around here. So how does this work? We've got a camera in each eyeball. So these are a highly miniaturized design that we actually developed in-house. A human eyeball average size is around 27 millimeters in diameter. By the time you account for the mechanics to move the eyeball, you end up with very little space left. So integrating a camera becomes a non-trivial task. It took us several years to get this design right. Why do we need cameras in the eyes? If you don't have cameras in the eyes, we tried it having, say, cameras mounted in the body, something like that. It's then a very, very difficult geometry problem to make sure that you've got a gaze that is focused in the right direction. So for a humanoid robot like this, it's absolutely essential that the robot makes eye contact and responds to me. So having cameras in the eyes is a way of greatly simplifying that task. We know that if a image of a face is centered in the camera image, then we have eye contact. Otherwise, we would have to calculate about 12 different angle rotations. You get stacked up errors, and you also get lag in the system. So the robot's always looking just behind where they should be looking. So if we have a look at some actual tracking here, so this robot's configured to look for fingers. It prefers one finger at the moment, and you'll see that the response is quite good. If I go too close, let's see, where are you? We'll see the robot lean back and go a little bit cross-eyed. So these kind of human-like responses are very important when you want a robot to interact with people. That is the absolute focus of what we're doing. Is Ameca a utility robot? No. Again, it's really about communications, talking to people. In a moment, I'm going to switch on some AI functions, and we'll try some conversation with Ameca and see how that goes. But before that, I just want to talk a little bit more about this idea of utility versus communication, entertainment, if you will. So robots are always a one-to-many proposition. So if you think about factory automation, you might have an expensive, say, KUKA, FANUC, or big industrial robot could cost up to £1 million. How do you justify the cost of that? It produces 10 million cars or 10 million consumer products. We're then looking at pennies per item produced. So if we think about humanoid robots in the same way, how can we get that kind of one-to-many value proposition? It's really about putting the robot in a place where there are lots of people. So if that robot can interact with 10,000 people in a day, then the cost of the robot becomes much more economical. You can justify the cost quite easily. The economics make sense. So where will you start to see these kind of robots? Public spaces, think shopping malls, airports, museums and theme parks. So these are the kind of spaces we're already working in. Where won't you see them? In your living room. Unless you're extremely wealthy, you're not going to be affording a robot like this. You've also got to look at the practical capabilities of the robot. So is this a walking robot? No, this robot is not actually mobile. Are we working on walking robots? Yes, we are. But what is the use case? So probably the best known bipedal walking robots are those produced by Boston Dynamics. If you've watched any of their videos, you'll know how fantastically impressive they are. Fantastic machines, wonderful to watch. But have you ever seen one in a real world use case? I haven't, and I don't believe Boston Dynamics have ever actually sold a biped commercially. Why is that? The technology just isn't there yet. We cannot do it in the reliable, cost-efficient, and safe kind of way that we would need to in order to make that a commercial proposition. One of the big engineering challenges in bipedal robots, or in fact all forms of humanoids, is actuation. We do not have an actuator that's comparable to human muscle. So human muscle has this fantastic property of its very, very fine force control. So forget about position. Everybody thinks in robotics, especially if you're used to working in industrial robotics, you think in terms of position control. So if you're used to CNC machines, position control is everything. It's all X, Y, Z, A, B, C rotations. This is not actually how living things work. I am vaguely aware of the position of things around me, but I do not know to the millimeter or sub-millimeter where everything is. If I went to pick up this glass of water that's in front of me, I didn't know the shape and size of the glass. How does that actually work? Force control. So we also have this property that we're able to become quite floppy. You won't see a floppy industrial robot. Does this matter? Yes, it really does matter if you're working on pick and place in an unconstrained environment. So these are some of the problems that need to be addressed for humanoids to find wider adoption in the marketplace. So a lot of people tend to think it's it's a question of AI, it's all about the clever software. Actually, it's not. The biggest problems are actually at the actuation level. If we could use a motor with no gearbox, we would have fantastic fine fidelity force control. The problem is we don't get enough torque. So we then have two options: either use a much bigger motor. So if I applied the right size motor for the forearm on Ameca here, I'd be looking at something probably about 150 millimeters diameter. Now you can immediately see that that's impractical. Even using the most efficient brushless DC motors, we would be looking at a very high current consumption. We'd be looking at a lot of weight because of the copper windings of the laminated armature. So motors are just electric brushless DC drives. DC drives are inherently pretty heavy. How did we actually solve this on Ameca here? Back to the pneumatics. So pneumatics, we established we could actually balance the load very well. So what you would find on Ameca is, let me just see if I can get it to do some more movement routine so you can get a better feel for this. One moment. Maybe you could find, I'll just hand that to you, Marcus, if you could just find the routine. I'm just looking for that exercise routine where it just moves through a number of more extreme poses, and we should be able to see that. There we go. Thank you. So we'll see these arms lifting up, and if you watch carefully, let's just flick back to the Teams video so I can see what's going on. Whoops, getting clobbered by robot here. We can see that we've got quite a wide range of actuation, and we can see the arms coming right up above horizontal. So in this kind of position, a lot of load on a motor. So how do we get away with using such small motors? So inside this arm, if we had a look, we would see a 22 millimeter diameter brush DC motor. We actually use Maxon motors in Ameca. The reason that we can get that amount of force out of it, there's a ball screw drive, which is very, very power efficient. So that's about 98% efficient in its power transmission. And B, we have this parallel actuation with the pneumatics. So the pneumatics can take about 90% of the load in the system, but very, very difficult to control for position. By superimposing this brush DC drive on top, we have very fine position control as well as the force control from the pneumatics. So I'm going to run out of time if I go on for too long, and I want to leave some space for some Q&A at the end. But before we go to that, I want to show some of the more advanced AI functions that we've been working on with Ameca. And I'm just going to enable some software for speech interaction. This is very early days, so if it doesn't work, please bear with me. Let's see what we actually get. Let's flick over here and start that one and start that one. And let's come back to here. Ameca, can you hear me?
Yes, I can hear you.
Oh, that's a good start. What are humanoid robots good at doing?
Humanoid robots are good at doing many things. They can help with tasks around the house, they can be used for research, and they can even be used in healthcare.
Well, I would probably disagree with tasks around the house. What about industrial?
Why would you disagree with that?
Because I don't think we have the actuators that are required.
What are actuators?
Aha, this is where I find the limits of your knowledge.
I apologize for not being able to answer your question. I am still learning and I will try to find an answer for you.
Can you tell me what a pneumatic cylinder is?
A pneumatic cylinder is a mechanical device that uses compressed air to generate linear motion.
Is it possible to achieve fine position control with a pneumatic cylinder?
Yes, it is possible to achieve fine position control with a pneumatic cylinder.
It's possible, but it's not easy.
No, it's not easy.
So this is quite a successful demo. It doesn't always work this well.
I'm sorry, I don't understand what you mean by this is quite. Could you please explain?
I'm just going to stop Ameca right there. There we go. So this is using, so Ameca is parsing information from the web and yeah, amalgamating all this together. Okay, so I've got a question from Nikki. Says, where do we see the technology being used in the future? So I really think it is going to be this kind of public spaces, places where the immediate ones I can think of. So a lot of the applications we're working on at the moment are to do with front office, front of house, so receptionist type applications. So imagine you came into a building and you're looking for a particular person or a particular area in the building. We can preload the robot with information about everybody who works there. We can even use facial recognition. They can have live interaction on the fly using, say, integration to Slack or Rocket Chat or text messaging or even SIP telephony. So lots of different ways that the robot can connect people to each other and people to the right information. And those are the applications we're looking at the moment. So receptionist, front of house, public locations, airports, amusement parks, theme parks, museums, shopping areas, those kind of things. Another question here, somebody's asking, what was the most challenging element of Ameca's development and what will the most difficult element in the, what's the most difficult element in future versions? So I would say, coming back to mechanical design, I think mechanical design is really one of the most difficult aspects. You'll notice when Ameca was moving, you might have seen that shoulder shrug, that we actually have motion on the clavicles as well as just in the shoulders. This is very unusual for a robot design, and it took us, I think, 6 different design iterations to get to that point. So versions 1, 2, 3, and 4 and 5. 5 just about worked. 1, 2, 3, and 4 were really too limited on the range. So we tried a lot of different mechanical configurations to get to this solution. Why didn't we just copy what human shoulder does? It's almost impossible because human shoulder is literally just joined by this tiny clavicle bone, and the whole rest of the connection is muscle tissue to shoulder blade. To emulate that in mechanics is really, really difficult. So you have this fluid mass of muscle that can generate huge forces. So I can move my shoulders around it and support loads. You know, I can lift 5 kilograms or more at full arm extension. So that was a huge challenge. Going forward, we are working on bipedal motion. Again, that's a huge challenge because of the actuator problem. If you want to have a look at our YouTube channel, You will see some videos of Byron, which was a bipedal walking robot project that we worked on over the last 5 years or so. I don't know what are you staring at? Are you looking at my... She gets fixated on certain things. Bipedal locomotion is a really big challenge, and that's one we're coming back to for Ameca. That's a kind of a long-term goal. It's not something you're going to see in a commercial product in the next year, or probably not even in the next 5 years. It's interesting to note, some of you, if you're interested in humanoid robotics, you may have heard a lot of talk from Tesla about Tesla bots. So Elon Musk is investing a lot of money into humanoid robots. Elon has a vision for using them in a factory setting. I'm a little bit dubious about that personally, because I think we already have very good factory automation, and I think what you tend to find, any of you who are used to working in a factory setting, you'll see the robots are very much designed for a particular task. So, and they are not human capable, they are superhuman as well. So I would say if you're building something that's equal to the capability of human, you're competing against 7.9 billion people that are already in the world. The cost to produce a human is actually quite low. They self-replicate, they self-repair, they last 100 years, they're super intelligent, and they can run off a bowl of muesli a day. So, you know, to compete with human level capability is extremely hard as an engineering challenge. If you look at things like, so Elon Musk, also known for Tesla and SpaceX, so you look at electric vehicles, nature doesn't make electric vehicles. Humans can't whiz down a motorway at 120 miles an hour. So those are superhuman type capabilities. So if you make a machine that can do that, you've outclassed humans very, very easily. So if you're working on a drone that can fly, you know, we don't have flying people. So technology that has superhuman capabilities, it's quite easy to identify the use cases, the economic rationale, the justification for it. When you are just sticking to human level functionality, then it's hard to make, I think, a rational use case for that. So any other questions do we have? And got a couple of minutes left. No, nothing coming up in the chat. So please do put any questions in the chat if you've got any more thoughts about this. So I'll talk a little bit more about Ameca itself, where we're going next. So this is generation 1. We have a roadmap for 4 generations. Generation 2, I already mentioned, goes to 97 actuators. Where do the improvements come? So in this version of Ameca, we only have very limited hand actuation, so we don't have any dexterous manipulation. There are only 4 actuators in the fingers. Generation 2 goes to 18 actuators in each hand, which gives us the ability to do pinch grips, grasping, picking up objects. So in the future, quite near future, you'll see Ameca playing chess and picking up objects and interacting with people in a more manual kind of way. The other place we're adding a lot more actuation is actually in the face. So you may have noticed when Ameca was talking that there are still some things we can do on lip sync. Lip sync is really important because actually it's a core communication tool. You don't realize how much you lip read until you find it really hard to understand without that. So those are that's the future roadmap. There's going to be a generation 3, generation 4. Please keep your eye on what we're doing. Follow our YouTube channel. connect on LinkedIn. If you're interested in what we're doing, please connect, and we'll share as much information as we can.